Okay, good morning all. So in the last class, we looked at the proof of third theorem, that is the regular languages, the class of regular languages is closed under the star operation. Every non-deterministic finite automaton has an equivalent deterministic finite automaton. So this is the theorem. First, let's write down the proof idea, and then we'll move on to the actual proof. So the proof idea is, as we discussed, each state in the DFA corresponds to the possible set of states in an NFA that can be reached from a given state on a given input symbol. So here this set of states is the important thing. Like we discussed yesterday, if there are, like in yesterday's example, there are 4 states in NFA, whereas ideally there will be 2 power 4 or 16 states in the corresponding DFA, of which some states we can ignore because they are either dead states or unreachable states. But ideally there are 16 states in the DFA because every state in the DFA corresponds to a possible set of states in the NFA. So every subset of the powers, every subset of Q in NFA becomes a state in DFA. And how many such subsets of Q are possible? 2 power cardinality of Q. Okay, so if K is the number of states of the NFA, it has 2 power k subsets of states. So can anyone tell me why the cardinality of the power set of a particular set is equal to 2 power the cardinality of the original set? So if k is the cardinality of q, why is the cardinality of power set of q 2 power k? Right. So it's quite straightforward. Suppose you have some k elements, all right, or k positions, k spaces, k places. Now, assume this is the place of the first element, second element, third element, and so on. Now, each element has a possibility of being in the set or not being in the set. Again, this one may be in the set or not in the set. So depending on each element being or not being in the set, you will get different subsets. So every particular combination of these sequences of zeros and ones, this is like a binary number with k bits, right? So 1 indicates that particular element is present in the set, 0 indicates that particular element is not present in the set. So every different number gives you a different set. And how many such different numbers are possible? 2 power k. So 2 power k different sets are possible. Okay, so this is basic combinatories which you would have learned in school. So that is the reason why the cardinality of the power set is 2 power the cardinality of the original set. Okay. Each subset corresponds to one of the possibilities that the DFA must remember. So the DFA simulating the NFA will have 2 power k states. We need to define the start state, the accept states, and the transition function of the DFA accordingly. So the proof idea is simple. If you have an NFA with k states, the corresponding DFA will have 2 power k states, each state in DFA corresponding to a subset of states in NFA. Since NFA with k states will have 2 power k subsets, each subset corresponds to a state in DFA, so DFA will have 2 power k states. Once that is done, now all you need to decide is what is the start state, what are the accept states, and what is the transition function. So this is the proof idea. Okay, so now let's get into the proof. let n equal to q sigma delta q naught and f be the NFA recognizing some language A. We construct a DFA m equal to q dash sigma delta dash q naught dash and f dash recognizing A. We first consider the case without epsilon arrows. And later take epsilon arrows into account. Okay, so first, what is q dash in terms of q? Exactly, q dash is nothing but power set of q. All right, sigma is the same as that of n. So delta will take some explanation. So this is this we discussed in last class also. For R belonging to q dash and A belonging to sigma, let delta dash RA equal to the set of q's such that q belongs to delta RA for some R belonging to R. Or another way of writing it is delta dash RA equal to union of delta RAs for each R belonging to R. So this is like sigma or sum in mathematics, union of the output sets. We discussed yesterday, right? Like if you take this example, say R is a set with 3 elements. Each of these elements in this set is like small r. So if you want delta dash R A for this entire set, you take each element. You take delta RA, delta A1, delta B1, delta D1. Each one is a set here. Perform the union of all these sets. You will get the final result. Okay? That's all. Same thing mentioned here. Okay. So let me make some space. Where union of delta Ra or belonging to R represents the union of the sets delta Ra for each possible R in R. Okay? Clear? Next, what is Q naught dash? What is the start state of the DFA? Same as start state of NFA. Is it correct? With the set of all the start states of NFA. What do you mean all the start states? How many start states does an NFA have? Yeah. It is a set with only one element, that is the start state of NFA. Okay. So Q naught dash is nothing but Q naught in a set. Okay. Every element in the DFA is a set. Every state in the DFA is a set. It is, even if it has single element, it is a set. Don't forget that. In this particular case, not regular DFA, which we began with in the course. When you're converting NFA to DFA, every state in the DFA is a set of states. Okay. And what is F dash? What are the final states in DFA? Subset of the power set in which all the final states of the NFA are included. Yes. So both are different statements. All the final states of NFA are, yeah, final state elements. Should all the elements be present? Yeah. So that's the thing. So all those states in which there is an accept state of NFA as an element, all those states are considered as final states in the DFA. Okay, so it is the set of R's such that R contains an accept state of N. Okay. Now, so the proof is done, assuming we are not dealing with epsilon arrows. So now we will extend the proof by including epsilon arrows. Okay. Now we will consider epsilon arrows. Now we'll consider epsilon arrows for any state R of M. We define E of R, that is set of all Q's such that Q can be reached from R by traveling along zero or more epsilon arrows. Okay, so in one of the earlier examples, if you remember, say delta of q1 comma 1 is q2, and delta of q2 comma epsilon is q3, right? So if you remember, I'm not sure if someone from this section or the other section asked, why are we not including q3 also in delta of q1 comma 1, right? Because the moment you are reaching q2, you are also automatically able to reach q3 without any more input, right? So q3 is sort of coming freely with q2. So why are you writing only q2 in the output of q1 comma 1? You should write both q2 and q3, right? When you get 1 as input to q1, you are reaching q2 as well as q3. So why are you writing only q2? So that case is covered now. When you use this notation, E of R. So when you write only delta, you write exactly only whatever next state you are going to, or next set of states you are going to. Okay. But if you also want to include the epsilon transitions, then you write it as E of that particular thing, E of delta q1 comma 1. So this will include not only q2 but all the other free states that come along with it. So once I reach q2, I can also reach some other states without reading any more input. So all those states will come in this output, that is q2 comma q3. Okay, so if you are given only delta, whether the input is 1 or epsilon or whatever it is, you write only the immediate output. But if you are asked for E of delta, this entire thing, then you include epsilon outputs also, states which are connected using epsilon arrows also. Okay, so we'll see this. This is just an example. I'll give one more example here. But before that, let me modify the transition function. Now, we modify the transition function as delta dash RA equal to set of Qs such that Q belongs to E of delta RA for some R belonging to R. So let's look at an example now. So let's assume there are 4 states. And Q1 on 1 goes to Q2, Q2 on epsilon goes to Q3, and Q3 on epsilon goes to Q4. This is not the entire machine. This is some sub portion of the machine. It doesn't matter what the rest of the machine is. This portion is enough for us to discuss the example. So delta Q1 comma 1 is Q2. right? Now E of delta of Q1 comma 1, what will this be? Huh? Q2, Q3, Q4 also or not? No. Yes or no? How many think yes? How many think no? Why no? So is it, simple question, is it coming freely with Q2 or not? Do you need to read any more input to reach Q4? No. So that will also come freely with Q2. So that should also be included. That's all. So Q2, Q3, Q4. All right. So, but first of all, delta of Q1 comma 1 is nothing but Q2 in a set. Okay. And E of delta RA, E of R is nothing but set of all those Qs that can be reached from R by traveling along 0 or more epsilon arrows. Okay, it need not be only one epsilon arrow. It can be 2, 3, 5, 10, 100, whatever they are, 0 or more epsilon arrows. Since 0 is also included, that particular state will also be included. Okay, so the state itself plus any states which it can reach using one or more epsilon arrows, all of those will also be included. All right. So this will be Q2, Q3, Q4. All right. Now suppose I just take E of Q1 comma Q2. Okay, then how will you do it? Will it be same? Really? How do you do this? Okay, so yeah, you're right. So we break it into E of Q1 union E of Q2. All right. What is E of Q1? Huh? Q2, Q3, Q4. What is the definition of E of R? It is the set of all those states which you can reach from R through 0 or more epsilon arrows. In this case, R is only Q1. So what all states can you reach from Q1 through 0 or more epsilon arrows? Q2. Q1, there is no epsilon arrow between Q1 and Q2. You can reach Q1 to itself using 0 epsilon arrows. That's it. Every state is by default included. Other states are included only if there is either direct or indirect epsilon arrows. From Q1, there are no epsilon arrows. So only Q1 is the output of E of Q1. Okay. So this is, yeah. Yes. So 0 epsilon arrows means what? Itself. Like even in the previous case, when I included Q2, Q3, Q4, you are fine with that. Why? Q2 can reach itself through 0 epsilon arrows. Okay. Union. What is this? E of Q2, Q2, Q3, Q4. So that is nothing but Q1, Q2, Q3, Q4. You see, the point is simple. Forget the definition of E and all that. E of Q1 comma Q2 means simple thing is from Q1 and Q2, what all states can I reach? Once I reach Q1 and Q2, what all states can I reach? Without taking any more input. Okay. So once I reach Q1, I cannot reach any more state without taking any more input. I can just be in Q1. Okay. I already reached Q1, so that will anyway be included. Once I reach Q2, without reading any more input, I can also reach Q3 and Q4. That's it. So from Q1 and Q2, without reading any more input, I can reach Q1, Q2, Q3, Q4. That's it. Okay. So the intuitive way of understanding that same thing is captured here mathematically, nothing more. So don't try to complicate it too much. Okay. So whatever states you are getting freely with the current state without reading any more input, only those states are included. If you are in Q1, are you getting any states freely without reading any more input? No. So only Q1 will be included. If you are in Q2, are you getting any more states freely? Yes. Q3 and Q4 plus Q2 because you are already in Q2. That's it. Okay. All right. Now, additionally, Q0 dash will be updated to. Now we are considering epsilon arrows also. Imagine if in an NFA from the start state, there are some epsilon arrows to some other states. So will the start state be Q0 only or something more? E of Q0 dash. No, we are defining Q0 dash. Again, think intuitively. If I have a start state and this start state is connected to some other states through epsilon arrows, it means I am getting those states also freely with the start state, right? So I should include all of them as my start state. So how do I write it? E of Q0, E of set Q0. That's all. No. Del of Q0 comma Y. See, basically E of Q0 is nothing but, you can think of it as E of del of Q0 comma epsilon. I mean 0 or more epsilons. So I can't, this is not exactly correct, but when you have epsilon as an input, you don't need to mention it, 0 or more epsilons as input. So you don't write delta, you just write the output of delta. Okay. E does not take ordered pair itself as input. E takes a set as input. So because the output of delta of some Q comma A is some set, we are able to give it as input to E. We cannot give Q comma A as input to E. No, we have to give delta of Q comma A because that will give me a set. So either I directly take the set or I give delta Q comma A as input. Okay, but E at any point of time takes a set as input, not a pair, not a tuple. Okay, so this will be E of Q0. All right. So additionally, Q0 dash is equal to this, will be the new start state which includes all the possible states sorry, that can be reached from the start state of n that is q naught along the epsilon arrows. Okay. So let's look at one more example. So let's say we have 4 states A, B, C, D. And let's say D is the final state, A is the start state. And okay. So can anyone tell me what will be Q naught dash? That is the start state of the equivalent DFA. What will that be? What? AB, CD. Set. Any other answers? ABCD. From A, you can reach all the other states through epsilon arrows. So all of them put together will be your start state. All right. So Q naught dash is E of A. All right. And what all states can be reached from A with 0 or more epsilon arrows? A itself, B, C, and D. All right. And let me ask you one more. Say delta dash B comma 1. What is this out? What is its output? C. Only C. That's all. Is it only C or CD? It is CD because it is no more delta of delta of B1. It is E of this. So E of delta B1 means first you expand the inner one. Delta B1 is what? C. So you have a set with only C as your element. Now that set is given as input to E, which means all the states which can be reached from C through 0 or more epsilon arrows will be the output. So C will anyway be included and D will be included. Okay, so is CD. All right. Okay. Clear or is it confusing? Yeah. So what is delta dash RA? So R is the set B here. Union of delta small ra for each small r in capital R. Here there is only one small r, that is B. Okay. If there are other elements, suppose this is maybe ABC, comma 1, then you will take delta A, comma 1, delta B, comma 1, delta C, comma 1 and perform their union. There is only one here. Okay. So delta B1, but this NFA includes epsilon arrows. So you should take E of this thing. Delta is for NFA. Delta dash is for the equivalent DFA. We are converting NFA to DFA. NFA's elements are Q, sigma, delta, Q naught, F. DFA's elements are Q dash, sigma, delta dash, Q naught dash, F dash. Okay. Why is delta dash? We defined, no? First, what we did? We first considered the case of converting NFA to DFA without epsilon arrows. Then we considered epsilon arrows also. And then we modified delta dash function. You see here. Now we modify the transition function as delta dash RA equal to set of all those Qs where Q belongs to E of delta RA. Earlier Q was belonging to delta RA. So from now we should follow this only. We should always include epsilon arrows. Okay. All right. Next, we will look at something called minimization of a DFA. This is simple, straightforward. Remove the dead and unreachable states. It does not affect the language recognized by the automata. So what are unreachable states? These are those states of a DFA which are not reachable from the initial state of the DFA on any input symbol. Okay. Then dead states a dead state is that non-final state you see, this is also an important condition. It is not sufficient if the state doesn't come out. It should also be important that it should be a non-final state. Dead state, what we understand, once you reach the state, you cannot come out of the state. That is our understanding of dead state. So it will not have any outgoing arrows except maybe a loop onto itself. All right. Only incoming arrows and then looping on itself, no outgoing arrows. This is called a dead state only if it is a non-final state, because sometimes a final state may also have no outgoing arrows. It may stop with itself and it may loop onto itself. It may not go out to any other state. Sometimes it may go out, sometimes it may not go out to any other state. But that does not make it a dead state. Final state is fine. If it is a non-final state and if it does not go to any other state, only then it is a dead state. Okay, so this condition is also important. A dead state is that non-final state of DFA whose transition on every input symbol terminates on itself that is Q is a dead state if Q is in capital Q minus F and delta of QA equal to delta of QA will be equal to delta of QA will be equal to Q. It should not go out of that state. It should loop onto itself. That's the only outgoing arrow it has. Or for every input symbol, every outgoing arrow will also end in itself. It does not go to any other state. That is a dead state, right? So delta of QA equal to Q for every A belonging to sigma. Okay. So this is how we minimize the DFA. Basically, even in the previous example where we converted NFA to DFA, although there are 16 states in total, we showed only 8 states. We said the remaining 8 states need not be shown. So basically what we did there is we minimized the DFA. Ideal DFA will have all the 16 states, but we minimize the DFA by ignoring dead states and unreachable states. Okay. So that's it for today. Let's stop here.